Hello and welcome to the Midnight Lab. Before we begin tonight's journey, take a moment to like the video and subscribe to the channel if you enjoy calm explorations of science and the strange forces that shape our universe. And while you're here, I'd love to know where in the world you're watching or listening from tonight. Are you somewhere beneath a quiet, clear sky, perhaps under drifting clouds? Or maybe you can hear the distant rumble of a storm outside your window. Wherever you are, the sky above you is never truly still. Even on the calmest night, the atmosphere above our heads is in constant motion, a vast ocean of air quietly shifting, flowing, and exchanging energy across the entire planet. Invisible rivers of wind stream through the upper atmosphere. Moisture rises and condenses into clouds. Tiny differences in temperature and pressure ripple outward and grow into storms that can stretch hundreds of miles across the sky. And sometimes, the atmosphere reveals its hidden machinery in spectacular ways. A bolt of lightning tears through the darkness, briefly heating the air hotter than the surface of the sun. A column of rotating wind twists down from a storm cloud and touches the ground. Ice forms inside towering thunderheads and falls to earth as stones of hail. In the far northern skies, shimmering curtains of green and purple light dance silently above the horizon. These phenomena can feel mysterious, even otherworldly. But beneath their drama lies something remarkable. They are the natural consequence of physics playing out on a planetary scale. Weather is not random chaos. It is the result of simple forces, heat, pressure, moisture, gravity, and motion, interacting inside one of the most complex systems on Earth. A delicate balance of energy from the sun, the rotation of our planet, and the restless movement of the atmosphere itself. In many ways, the air surrounding us behaves like a living system. It organizes itself. It circulates energy from one place to another. It creates patterns that repeat across continents and oceans, and yet no two storms are ever exactly the same. For centuries, scientists have tried to understand this restless sky. From early observers mapping wind patterns across the oceans, to modern satellites watching storms spiral across entire hemispheres, each generation has uncovered another piece of the puzzle. And the deeper we look, the stranger the atmosphere becomes. Lightning that shoots upward into space, storms that organize themselves like giant engines, electrical currents that quietly circle the entire planet, invisible waves of air that steer storms across continents, and delicate ice crystals that bend sunlight into halos and shimmering pillars of light. Tonight, we're going to explore the strange science of weather phenomena, not just what they look like, but how and why they form. We'll move from the quiet physics of clouds to the violent power of thunderstorms, from the hidden rivers of wind high above the earth to the luminous auroras that connect our atmosphere to the sun itself. And as we do, something fascinating begins to emerge. All of these strange events, lightning, tornadoes, hurricanes, glowing auroras, are not separate mysteries. They're all part of the same system, a thin, shifting layer of air that wraps around our planet, quietly turning sunlight into wind, clouds, storms, and light. So settle in, get comfortable, and let's begin our journey into the strange and beautiful physics of Earth's atmosphere. Because the next time you look up at the sky, you might realize it's doing far more than just holding up the clouds. If you step outside on a calm night and look up at the sky, it can feel wonderfully still. The stars seem fixed, the clouds drift slowly if they are there at all, and the air feels quiet and unmoving. Yet this calm impression hides something remarkable. The atmosphere surrounding our planet is one of the most active and complex physical systems on Earth. Even during the most peaceful evening, the air above you is constantly shifting, exchanging energy, and reorganizing itself in ways that stretch across the entire planet. One way to understand this restless motion is to think of the atmosphere not as empty space filled with air, but as a living system of energy flows. Heat, moisture, and momentum move through it continuously. Tiny disturbances can grow into storms. Invisible waves of motion travel through the upper sky. Vast rivers of wind circle the globe. In physics, systems like this are often described as being far from equilibrium. In simple terms, equilibrium is a state of balance where nothing changes very much. A cup of water sitting on a table eventually reaches equilibrium with the room around it. Its temperature stabilizes and nothing dramatic happens. The atmosphere is very different. It is constantly being pushed away from equilibrium by the energy of the sun. Every moment sunlight pours onto the surface of Earth, warming land, ocean, and air. This heating does not happen evenly. The equator receives far more solar energy than the polar regions. Land warms faster than water. Dark forests absorb heat differently than bright deserts or snow-covered ground. These uneven patterns of heating create differences in temperature across the planet, and wherever temperature differences exist, motion begins. Warm air expands and becomes less dense. Cooler air contracts and becomes heavier. The result is that warm air tends to rise while cooler air sinks. These vertical movements may start gently, but they form the foundation of all weather. This constant flow of energy through the atmosphere is what scientists call a thermodynamic system. In fact, the atmosphere behaves very much like a gigantic heat engine. It takes in energy from the sun, moves that energy around through winds and storms, and eventually releases it back into space as infrared radiation. The concept of systems organizing themselves under these kinds of conditions was explored by the physicist Ilya Prigogine. During the 20th century, Prigogine studied what he called dissipative structures. These are patterns that spontaneously emerge in systems that are continuously supplied with energy. In such systems, order can appear naturally out of motion and instability. A whirlpool forms in flowing water. Convection cells appear in heated fluids. Patterns arise without any external designer simply because energy is passing through the system. The atmosphere behaves in much the same way. Storms, wind belts, and cloud systems are not carefully arranged structures. They are patterns that emerge from the continuous flow of solar energy through Earth's atmosphere. As long as the sun keeps shining and the planet keeps rotating, these patterns will continue to form and evolve. This is why weather can feel chaotic yet still follow clear physical laws. The word chaos in science does not mean randomness. Instead, it describes systems that are extremely sensitive to small changes. Even tiny differences in starting conditions can grow into large differences later on. One of the scientists who helped reveal this property of the atmosphere was the American meteorologist Edward Lorenz. In the early 1960s, Lorenz was working with one of the first computer models designed to simulate atmospheric circulation. His goal was to understand how weather patterns might evolve over time. While running one of his simulations, Lorenz decided to repeat an earlier calculation. To save time, he entered starting numbers that were rounded slightly from the original values. The difference was extremely small, less than 1,000th. Yet as the model ran forward in time, the weather patterns produced by the simulation diverged completely from the original results. From this discovery came the famous idea sometimes called the butterfly effect. The phrase suggests that the flap of a butterfly's wings could eventually influence the formation of a distant storm. Whether or not butterflies truly cause storms is not the point. The lesson is that the atmosphere is a nonlinear system, meaning that small changes can grow dramatically over time. This sensitivity explains why predicting weather becomes more difficult the farther we look into the future. Even with powerful computers and satellites observing the planet, the system itself is inherently complex. Despite this complexity, large-scale patterns still emerge across the globe. One of the earliest scientists to recognize these patterns was Edmund Halley, an English astronomer better known for the comet that bears his name. In the late 1700s, Halley studied wind patterns across the Atlantic Ocean. He noticed that winds in tropical regions tend to blow steadily from the east. These winds became known as the trade winds because they powered sailing ships traveling between continents during the Great Age of Exploration. Halley believed these winds were caused by the daily heating of the sun as it moved across the sky. Although his explanation was not entirely correct, his observations were an important step toward understanding global atmospheric circulation. A few decades later, another scientist offered a clearer explanation. George Hadley, an English lawyer with a strong interest in natural philosophy, proposed that warm air rising near the equator must eventually move toward the poles. As this air travels north or south, Earth's rotation causes the moving air to curve sideways. The result is a system of large circulating loops in the atmosphere, now called Hadley cells. Within these circulation cells, warm air rises near the equator, flows poleward high in the atmosphere, sinks in subtropical regions, and then returns toward the equator near the surface. This continuous movement redistributes heat from the warm tropics toward cooler parts of the planet. Without this atmospheric circulation, the equator would grow unbearably hot while the polar regions would become far colder than they already are. In this sense, the atmosphere acts as Earth's global climate regulator. Winds carry heat across continents and oceans. Clouds reflect sunlight back into space while trapping some warmth below. Storms transport moisture from the sea to the land. Every one of these processes contributes to balancing energy across the planet. The atmosphere may appear chaotic, but underneath that chaos lies an elegant physical purpose. It is constantly attempting to smooth out temperature differences created by the uneven heating of the sun. Whenever a region becomes warmer than its surroundings, the atmosphere begins to move energy away from that location. When one area cools more quickly than another, winds form to rebalance the difference. The result is a dynamic system that never quite settles down. Storms form, release their energy, and dissipate. New cloud systems gather. Winds shift direction. The entire atmosphere is perpetually adjusting itself. Seen from space, these adjustments become beautifully visible. Satellite images reveal spiraling cyclones stretching across entire oceans. Long bands of clouds trace the invisible pathways of jet streams. Vast plumes of dust and moisture move slowly across continents. Each of these patterns is a natural response to energy moving through the atmosphere. And although we experience weather as isolated events, a thunderstorm here, a windy day there, every one of these events is connected to the same planetary system. The gust of wind that rustles a tree in one city may ultimately be linked to temperature differences thousands of miles away. The sky above us is not merely a backdrop to life on Earth. It is an active, self-organizing system that shapes the environment of the entire planet. And as we continue to explore its strange and powerful phenomena, from lightning to hurricanes to shimmering auroras, it helps to remember that all of them begin with this same restless engine of air, heat, and motion that quietly surrounds us every moment of our lives. To understand why weather behaves the way it does, it helps to look beneath the clouds and winds and focus on something more fundamental. Weather is not simply the movement of air, it is the movement of energy. And the branch of science that studies how energy moves through physical systems is called thermodynamics. Thermodynamics may sound intimidating at first, but the underlying ideas are surprisingly intuitive. At its heart, thermodynamics describes how heat, temperature, pressure, and energy interact. These relationships govern the behavior of everything from steam engines to refrigerators. They also govern the behavior of Earth's atmosphere. Air may feel light and invisible, but physically it behaves just like any other fluid. It has mass, it occupies space, and it responds to forces. Most importantly, its properties change when it is heated or cooled. One of the most important relationships in atmospheric physics involves temperature, pressure, and density. When air warms, its molecules move more rapidly and spread farther apart. As a result, warm air becomes less dense. When air cools, its molecules slow down and pack closer together, making the air denser. This simple difference creates motion. Less dense air tends to rise because it is buoyant relative to the surrounding air. Denser air tends to sink. The process is similar to what happens when a bubble rises through water or when hot air lifts a balloon. Meteorologists often describe this relationship using a simplified expression derived from the ideal gas law. In words, the relationship can be expressed as pressure equals density multiplied by the gas constant multiplied by temperature. This means that when temperature changes, either density or pressure must adjust in response. In the atmosphere, these adjustments occur constantly. Imagine a patch of ground that becomes warmed by sunlight during the day. The air just above that surface begins to warm as well. As it warms, it expands and becomes less dense. Eventually it becomes buoyant enough to rise upward. As that parcel of air rises, something interesting happens. The surrounding atmospheric pressure decreases with height. Near sea level, the weight of the entire atmosphere presses downward, creating relatively high pressure. Higher in the sky, there is less air above, and therefore the pressure is lower. When rising air enters this lower pressure environment, it expands. An expansion requires energy. The energy needed for that expansion comes from the internal heat of the air itself. The result is cooling. This process is known as adiabatic cooling. The word adiabatic simply means that the temperature change occurs without exchanging heat with the surrounding environment. Instead, the temperature change happens because the air parcel expands or compresses. Meteorologists measure this cooling using what is called the lapse rate, which describes how temperature changes with altitude. When unsaturated air rises, meaning the air does not yet contain enough moisture to form clouds, It cools at what is called the dry adiabatic lapse rate. This rate is approximately 10 degrees Celsius per kilometre of altitude. In other words, if a parcel of dry air rises about 1 kilometre into the atmosphere, its temperature will drop by roughly 10 degrees Celsius. This steady cooling plays a crucial role in cloud formation. As rising air cools, the water vapour it contains begins to approach a point known as saturation. When the air reaches saturation, the water vapour begins to condense into tiny droplets, forming clouds. At that moment, the physics changes slightly. Condensation releases energy that had been stored in the water vapour. This energy is called latent heat. The word latent simply means hidden, because the heat was stored invisibly within the vapour before condensation occurred. When condensation begins, this latent heat is released into the surrounding air. The extra energy slows the rate at which the rising air cools. From that point onward, the air cools according to the moist adiabatic lapse rate rather than the dry one. This rate is typically around 6 degrees Celsius per kilometre, although the exact value varies depending on moisture content. This difference may seem small, but it has enormous consequences for weather. The release of latent heat acts like an invisible energy boost for rising air. It makes the air parcel warmer than its surroundings, allowing it to continue rising higher and higher into the atmosphere. This process is one of the main drivers of thunderstorms. When warm, moist air rises and condensation releases large amounts of latent heat, the rising air can accelerate dramatically. In powerful storms, these updrafts can reach speeds of more than 50 meters per second. That is fast enough to lift large hailstones and keep them suspended inside storm clouds. The energy involved in these processes is surprisingly large. A single mature thunderstorm can release energy comparable to several nuclear power plants operating simultaneously. Much of that energy originates from water vapor. To understand why moisture plays such a powerful role in weather, scientists rely on a relationship known as the Clausius-Clapeyron relation. This principle describes how the amount of water vapor the atmosphere can hold changes with temperature. In simple terms, warmer air can hold much more moisture than cooler air. The Clausius-Clapeyron relation shows that for every degree Celsius increase in temperature, the atmosphere can hold roughly 7% more water vapor. This means that even modest warming can significantly increase the amount of moisture available in the air. More moisture means more potential for condensation. More condensation means more latent heat release. And more latent heat release means stronger storms. This chain of events is why warm tropical oceans often produce the most intense storms on Earth. The warm air above these oceans contains enormous quantities of water vapor. When that vapor condenses inside developing storm systems, vast amounts of energy are released. Meteorologists often describe this process as fueling atmospheric convection. One scientist who explored the energetic structure of weather systems in great detail was Edward Norton Lorenz. Beyond his work on chaos theory, Lorenz also studied the flow of energy through the atmosphere. He helped describe how energy moves between different forms, such as potential energy stored in temperature differences and kinetic energy expressed as wind. Lorenz demonstrated that weather systems essentially convert stored energy into motion. Temperature differences between regions create potential energy, and atmospheric circulation transforms that potential energy into winds and storms. In other words, weather is the atmosphere's way of redistributing energy. Another important figure in understanding these dynamics was Norman Phillips. In the 1950s, Phillips developed one of the first successful computer models of atmospheric circulation. His model simulated how temperature differences could produce realistic patterns of winds and pressure systems. Phillips showed that even relatively simple equations could generate surprisingly lifelike atmospheric behavior. His work helped launch the field of numerical weather prediction, which today relies on powerful supercomputers that simulate the atmosphere in remarkable detail. Yet even with all our technology, the underlying principles remain elegantly simple. Warm air rises, cool air sinks. Pressure differences drive winds, water vapor stores and releases energy, and the atmosphere constantly works to balance uneven heating across the planet. These principles form the thermodynamic foundation of weather. Every cloud drifting across the sky, every gust of wind, and every distant thunderstorm is shaped by these quiet exchanges of heat and motion. And although the atmosphere may sometimes appear chaotic or unpredictable, its behavior ultimately follows the same physical laws that govern boiling water in a kettle or warm air rising above a candle flame. The difference is that in the atmosphere, these processes unfold on a planetary scale. quietly transforming sunlight into motion, clouds and storms high above our heads. If you watch the sky for long enough, clouds begin to reveal themselves as something more than decoration. They drift, gather, stretch, and dissolve in an endless dance above the landscape. Sometimes they appear as thin wisps high in the blue, sometimes as thick grey blankets that soften the sunlight, and sometimes as towering white structures that look almost like mountains floating in the air. Despite their gentle appearance, clouds are one of the most important features of Earth's atmosphere. They are the visible expression of water moving through the air, and they play a central role in weather, climate, and the transfer of energy across the planet. At their most basic level, clouds form through a simple physical process. Warm air rises, the rising air cools, and water vapor condenses into tiny droplets. But the details of that transformation are surprisingly intricate. Air around us always contains some amount of water vapor. Even in very dry regions, there are still countless invisible molecules of water, floating among the nitrogen and oxygen that make up most of the atmosphere. When air warms, it can hold more water vapor. When it cools, its capacity to hold that vapor decreases. This is a direct consequence of the thermodynamic relationship described earlier by the Clausius-Clapeyron relation. As warm air rises through the atmosphere, it expands and cools through the process known as adiabatic cooling. Eventually, the temperature of that rising air may drop to a point called the dew point. The dew point is the temperature at which the air becomes saturated, meaning it can no longer hold all of its water vapor in gaseous form. At that moment, condensation begins. Water vapor molecules start gathering together, transitioning from invisible gas into tiny liquid droplets. Each of these droplets is extremely small, often only about 10 micrometers across, which is roughly 1/10 the width of a human hair. Even though each droplet is tiny, a cloud may contain billions or even trillions of them suspended in the air. Yet condensation does not occur easily in perfectly clean air. Water molecules need something to gather around. In the atmosphere, they usually condense onto microscopic particles known as aerosols. These aerosols can come from many sources. Tiny grains of desert dust lifted by wind, salt crystals thrown into the air by breaking ocean waves, particles released from forest fires, even microscopic fragments of biological material such as pollen or bacteria. When water vapor condenses onto one of these particles, the particle becomes what scientists call a cloud condensation nucleus. Atmospheric chemist Susan Solomon, whose research has helped illuminate many aspects of atmospheric chemistry and climate science, has often emphasized how surprisingly important these tiny particles can be. Without aerosols acting as condensation nuclei, cloud formation would be far less efficient. The atmosphere is therefore not only a mixture of gases, but also a delicate suspension of microscopic particles that influence how clouds form and evolve. Once condensation begins, clouds become visible because the tiny droplets scatter sunlight. Light entering a cloud is reflected in many different directions by the countless droplets inside it. This scattering gives clouds their bright white appearance when illuminated by the sun. Although clouds may seem light and weightless, they actually contain enormous amounts of water. A typical cumulus cloud might hold several hundred tons of liquid water. That sounds dramatic, but the water is spread across such a large volume that the droplets remain suspended by gentle air currents. In many cases, rising air within the cloud continues to lift the droplets upward, keeping them aloft even as gravity quietly pulls downward. Clouds are therefore both physical structures and dynamic processes. They're constantly forming, changing shape, and dissipating as air flows through them. One of the first people to recognize the importance of cloud shapes was an English pharmacist and amateur meteorologist named Luke Howard. In the early 1800s, Howard developed a systematic way to classify clouds based on their appearance. He introduced several names that are still used today. The word cirrus comes from the Latin word for curl or tuft. Cirrus clouds appear as thin, wispy strands high in the atmosphere, often composed of ice crystals drifting at altitudes of several kilometers. Stratus clouds form broad, flat layers that spread across the sky like a blanket. These clouds often produce overcast conditions and can bring light drizzle or mist. Cumulus clouds appear as rounded, puffy structures with bright tops and darker bases. They often resemble cotton balls floating against the blue sky. When cumulus clouds grow vertically and develop into towering storm clouds, they become cumulonimbus clouds. These are the clouds capable of producing thunderstorms, lightning, heavy rain, and sometimes hail or tornadoes. Luke Howard's classification system was simple yet powerful. By naming clouds according to their shapes and structures, he provided meteorologists with a shared language for describing the sky. Even today, observing cloud types remains one of the easiest ways to understand what the atmosphere is doing. High cirrus clouds may indicate that a large weather system is approaching. Low stratus clouds often signal stable atmospheric conditions with little vertical motion. Tall cumulus clouds suggest that warm air is rising vigorously, potentially leading to storms later in the day. Beyond their visible shapes, clouds also contain subtle physical processes that control how precipitation forms. One particularly important mechanism is known as the Bergeron-Findeisen process, named after the scientists Tor Bergeron and Walter Findeisen. This process occurs in mixed-phase clouds that contain both supercooled water droplets and tiny ice crystals. Supercooled water is liquid water that remains unfrozen even though its temperature is below the normal freezing point. In the atmosphere, supercooled droplets can exist at temperatures well below 0 degrees Celsius. In mixed-phase clouds, something curious happens. Water vapor tends to deposit onto ice crystals more readily than onto liquid droplets. This happens because the equilibrium vapor pressure over ice is slightly lower than the vapor pressure over liquid water. In practical terms, this means that water vapor slowly migrates toward ice crystals and away from nearby droplets. As a result, the ice crystals grow larger while the surrounding droplets gradually shrink. Over time, the growing ice crystals become heavy enough to fall. As they fall through warmer layers of the atmosphere, they may melt and reach the ground as rain. This subtle interaction between droplets and ice crystals plays a major role in producing precipitation in many types of clouds. Clouds therefore serve as laboratories of atmospheric physics. Within their shifting boundaries, condensation, evaporation, freezing, melting, and turbulent mixing all occur simultaneously. Sometimes these processes remain gentle and quiet, producing soft layers of cloud that drift slowly across the sky. At other times, especially when strong rising air currents are present, clouds grow vertically into enormous towers that reach high into the atmosphere. Those towering cumulonimbus clouds are the birthplace of some of the most dramatic weather on Earth. Inside them, powerful updrafts carry moisture upward, while falling rain and ice create downdrafts below. Electrical charges separate, leading to lightning. Ice particles collide and grow into hail. Rotating winds may begin to organize within the storm. All of that complexity begins with the simple act of rising air cooling and water vapor condensing into droplets. From these humble beginnings, the sky builds structures that can stretch miles into the atmosphere and influence weather across entire regions. So the next time you look up and see clouds drifting across the sky, you're not just seeing shapes in the air. You're seeing the visible signature of the atmosphere at work, quietly transforming invisible water vapor into one of the most dynamic and beautiful phenomena in the natural world. On warm afternoons, especially in regions where the air is humid and the ground has been soaking up sunlight all day, the atmosphere sometimes begins to reorganize itself in a very dramatic way. Small puffy clouds may start appearing overhead, almost casually at first, as though the sky is experimenting with a few gentle brushstrokes. But over time, those clouds may grow taller, thicker, and darker, gradually transforming into towering structures that rise many kilometers into the atmosphere. What begins as a quiet column of rising air can eventually grow into a thunderstorm. Thunderstorms are among the most energetic weather systems that regularly occur on Earth. At their core, they are powered by a process known as convection. Convection is the movement of heat through the motion of fluids, and in the atmosphere that fluid is air. When warm air near the surface becomes buoyant enough to rise, it begins carrying energy upward. As the air climbs higher into the troposphere, it cools and releases moisture through condensation, forming clouds. If the conditions are favourable, the rising motion continues and intensifies. This vertical transport of heat and moisture makes thunderstorms behave remarkably like giant atmospheric engines. In fact, many meteorologists describe thunderstorms as convective heat engines. The energy that drives them originates from the uneven heating of Earth's surface by the sun. Warm air near the ground stores thermal energy, and the storm acts as a mechanism that transports that energy upward into the higher atmosphere. As warm air rises, cooler air descends nearby to replace it. This circulation allows the storm to continue operating as long as the energy supply remains available. The entire process unfolds within the lowest region of the atmosphere known as the troposphere. The troposphere extends from the surface of the planet upward to roughly 10 to 12 kilometers in altitude, depending on latitude. Nearly all weather occurs within this layer because it contains most of the atmosphere's water vapor and experiences the strongest vertical temperature gradients. For convection to become powerful enough to produce thunderstorms, the atmosphere must contain a certain amount of instability. Atmospheric instability occurs when rising air continues to remain warmer and less dense than the surrounding environment. If a rising parcel of air becomes cooler than the surrounding air, it will slow down and eventually sink. But if it stays warmer than its surroundings, it will continue rising, sometimes accelerating dramatically. Meteorologists measure this potential for rising motion using a quantity called convective available potential energy, often shortened to CAPE. Convective available potential energy represents the amount of energy available to accelerate rising air parcels upward through the atmosphere. It is essentially a measure of how unstable the atmosphere is. Higher values of CAPE indicate that the atmosphere contains more stored energy that can be released through convection. In strong thunderstorm environments, CAPE values may reach several thousand joules per kilogram. In practical terms, that means rising air parcels can accelerate upward with considerable force. These powerful updrafts can reach speeds of more than 50 meters per second in extreme storms, that is fast enough to carry large quantities of moisture high into the atmosphere and to keep heavy hailstones suspended inside the storm cloud. The rising motion inside a thunderstorm is not smooth or gentle. Instead, it is filled with turbulence. Turbulence refers to chaotic and irregular motion within a fluid. Rather than flowing smoothly in straight lines, turbulent air swirls, twists and mixes in complex patterns. Small eddies interact with larger eddies, creating a cascade of motion across many different scales. One of the scientists who studied turbulence in detail was the Russian mathematician Andrei Kolmogorov. In the 1940s, Kolmogorov developed a statistical theory describing how energy moves through turbulent fluids. According to Kolmogorov's theory, energy injected into a fluid at large scales gradually breaks down into smaller and smaller swirls of motion. This process is sometimes called the turbulent energy cascade. Within a thunderstorm, large rising currents of air break apart into countless smaller turbulent eddies. These swirling motions mix air, moisture, and temperature differences throughout the cloud. Although turbulence may appear chaotic, it plays an essential role in distributing energy inside the storm. It helps transport heat upward, spreads moisture throughout the cloud, and contributes to the development of complex internal structures. The detailed study of convective storms was advanced significantly by meteorologist Joanne Simpson. Simpson was one of the first scientists to investigate tropical convection using both aircraft observations and early satellite data. Her work during the 1950s and 1960s helped reveal the internal organization of convective cloud systems. Simpson showed that thunderstorms are not simply random bursts of rising air, but structured systems with identifiable components. Inside a typical thunderstorm, the rising motion forms a powerful updraft. This updraft carries warm, moist air upward, where condensation forms towering cumulonimbus clouds. At the same time, falling precipitation creates a downward flow of cooler air known as a downdraft. The interaction between updrafts and downdrafts gives thunderstorms their distinctive structure. The updraft acts as the storm's engine, transporting heat and moisture upward. The downdraft returns cooler air toward the surface, often producing gusty winds when it reaches the ground. This continuous circulation allows the storm to maintain itself for a period of time. As long as warm, moist air continues to feed the updraft, the storm can remain active. Within this environment of rising air, falling rain, and turbulent mixing, the stage is set for several other remarkable atmospheric phenomena. One of the first consequences of strong updrafts is the formation of large cloud towers that can extend several kilometers above the ground. At these heights, temperatures drop well below freezing, allowing ice crystals to form. Collisions between ice particles, supercooled droplets, and graupel begin to occur inside the cloud. These collisions separate electrical charges, eventually producing the powerful electrical discharges we know as lightning. At the same time, the vigorous updrafts may carry ice particles upward repeatedly through different temperature layers of the storm. With each cycle, additional layers of ice accumulate around the particles, gradually forming hailstones. In some particularly intense storms, rotating wind patterns may begin to develop. Wind shear, which occurs when wind speed or direction changes with height, can tilt and stretch rotating tubes of air within the storm. Under the right conditions, these rotations may concentrate and strengthen, potentially leading to the formation of tornadoes. All of these dramatic phenomena originate from the same fundamental mechanism: convection. A thunderstorm begins with nothing more than rising warm air. Yet once convection starts organizing energy within the atmosphere, a complex system emerges. Energy that was originally stored as heat near the ground becomes converted into vertical motion, turbulence, electrical charge separation, and powerful winds. Moisture carried upward becomes clouds, rain, hail, and lightning. Seen from a distance, a mature thunderstorm often appears as an enormous cloud tower with a flattened top spreading outward like an anvil. This shape forms when the rising air reaches the upper boundary of the troposphere and spreads sideways beneath the stable layer above. From that vantage point, the storm reveals itself as a massive engine operating within the atmosphere. Warm air flows in near the base, energy moves upward through the storm's core, and cooler air spreads outward at high altitude. Eventually, the storm exhausts its available energy and begins to weaken, allowing the atmosphere to return temporarily toward a calmer state. Yet somewhere else, another region of warm air may already be rising, quietly preparing to repeat the cycle. In this way, thunderstorms serve as one of the atmosphere's most powerful tools for redistributing energy. They transport heat and moisture upward, mix the air through turbulence, and release enormous quantities of latent heat into the surrounding environment. What may appear from the ground as a sudden burst of dramatic weather is actually part of a much larger planetary process. The atmosphere is constantly working to balance itself, moving energy from warmer places to cooler ones, and thunderstorms are one of the most efficient ways it accomplishes that task. Within the towering clouds of a thunderstorm, something remarkable is quietly taking place. Alongside the swirling winds, rising air, and growing droplets of water and ice, an electrical process is unfolding. Invisible charges begin to accumulate, separating into different regions of the cloud until the tension between them becomes strong enough to break the insulating power of air itself. The result is lightning. Lightning may appear sudden and chaotic when viewed from the ground, but it is actually the outcome of a very specific physical mechanism that develops inside storm clouds. To understand how it forms, it helps to look closely at what is happening inside the turbulent interior of a thunderstorm. Within a mature storm cloud, powerful updrafts lift warm, moist air upward through regions where temperatures drop well below freezing. As the rising air cools, water vapor condenses and forms droplets. Higher in the cloud, those droplets freeze into tiny ice crystals. At the same time, other particles known as graupel begin to form. Graupel consists of small lumps of ice created when supercooled water droplets freeze onto snow crystals. These graupel particles are heavier and more irregular in shape than delicate ice crystals. Inside the storm, strong updrafts and turbulent mixing cause ice crystals, graupel, and droplets to collide with one another constantly. These collisions do more than simply rearrange ice particles, they also transfer electrical charge. Laboratory experiments and field observations have shown that when ice crystals collide with graupel under the cold conditions found inside thunderstorms, the particles tend to exchange electrical charge. Typically, the lighter ice crystals acquire a positive charge, while the heavier graupel particles become negatively charged. Because the lighter ice crystals are carried upward by the storm's rising currents, they accumulate near the top of the cloud. The heavier graupel particles fall or remain suspended in the middle regions of the storm. This process gradually separates electrical charges within the cloud. Over time, the upper portion of the storm becomes strongly positively charged, while the middle and lower regions accumulate negative charge. The separation can grow extremely intense. The electrical potential difference between these regions may reach hundreds of millions of volts. The atmosphere normally acts as an electrical insulator. Under ordinary conditions, air resists the flow of electric current. But when the electric field inside a storm becomes strong enough, the insulating properties of air begin to break down. When that happens, a rapid electrical discharge occurs. Lightning begins with the formation of a faint branching channel of ionized air called a stepped leader. This channel propagates downward from the cloud in short bursts, creating a zigzag path through the air. The stepped leader is usually invisible to the naked eye because it is relatively dim. As it approaches the ground, the electric field near the surface intensifies. Objects on the ground, including trees, buildings, and even the Earth's surface itself, respond by sending upward streamers of positive charge. When one of these upward streamers connects with the descending leader channel, the electrical circuit is completed. At that instant, an enormous current surges through the channel in what is known as the return stroke. This is the brilliant flash of lightning that we see. The temperature inside the lightning channel rises extraordinarily quickly. In a fraction of a second, the air is heated to temperatures approaching 30,000 degrees Celsius, which is several times hotter than the surface of the sun. This sudden heating causes the air to expand explosively, producing the shock wave that we later hear as thunder. Although lightning often appears as a single flash, it frequently consists of multiple rapid discharges travelling along the same channel. The flickering effect that we see during a lightning strike reflects this series of electrical pulses. For many years, scientists wondered how lightning inside individual storms might connect to the larger electrical environment of the planet. One of the first researchers to explore this question was the Scottish physicist Charles Thomson Rees-Wilson, usually known as CTR Wilson. Wilson was deeply interested in atmospheric electricity and the processes that occur inside clouds. In the early 20th century, Wilson developed the cloud chamber, a device that allowed scientists to observe the paths of charged particles as they moved through supersaturated vapor. The cloud chamber later became an important tool in particle physics, but Wilson originally designed it to study cloud formation and atmospheric electricity. Through his investigations, Wilson proposed that thunderstorms might act as generators in a global electrical system. His insight eventually led to the concept known today as the global electric circuit. The global electric circuit describes the atmosphere as a vast electrical system that connects thunderstorms, fair weather regions, the Earth's surface, and the ionosphere. The ionosphere is a region of the upper atmosphere beginning roughly 60 kilometers above the ground. At these altitudes, solar radiation ionizes atmospheric gases, creating layers filled with electrically charged particles. The ionosphere therefore behaves somewhat like a conducting shell surrounding the planet. Meanwhile, the Earth's surface also acts as a conductor because of its moisture content and mineral composition. Between these two conducting layers lies the atmosphere, which under most conditions behaves as a weak electrical resistor. Thunderstorms play a central role in maintaining this system. Each storm effectively pumps electrical charge upward toward the ionosphere through lightning and other electrical processes. Globally, there are typically around 2,000 active thunderstorms occurring at any given moment across the planet. Together, they maintain a steady electrical potential difference between the Earth's surface and the ionosphere. This voltage difference averages around 250,000 volts. In fair weather regions far from storms, a small but continuous electric current flows downward from the ionosphere toward the ground. The current is extremely weak, only a few picoamperes per square meter, but it exists everywhere across the planet. This gentle electrical flow completes the circuit that thunderstorms help sustain. Lightning does more than simply balance electrical charges in the atmosphere. It also plays a role in atmospheric chemistry. When lightning heats air to extremely high temperatures, the intense energy breaks apart molecules of nitrogen and oxygen. These atoms recombine to form compounds known as nitrogen oxides. Nitrogen oxides eventually dissolve in rainwater and fall to the surface as nitrates. These nitrates act as natural fertilizers that enrich soils and support plant growth. Long before modern agriculture introduced synthetic fertilizers, lightning was one of the natural mechanisms that helped replenish nitrogen in ecosystems. In this way, thunderstorms contribute not only to weather, but also to the chemistry of life on Earth. Even today, scientists continue studying lightning in greater detail using modern technology. One particularly advanced instrument is the Atmosphere Space Interactions Monitor, often shortened to ASIM. This instrument was developed by the European Space Agency and installed on the International Space Station. ASIM observes lightning and other electrical phenomena from orbit, allowing scientists to study storms from above. The instrument also detects unusual events such as sprites, blue jets, and other luminous flashes that occur high above thunderstorm clouds. These discoveries have revealed that lightning is only part of a much larger electrical environment, extending upward into the upper atmosphere. What appears from the ground as a single flash of light is actually part of a global electrical network connecting storms, clouds, the ionosphere, and the planet itself. The next time lightning flickers across the sky during a distant storm, it may help to remember that the flash is not merely a local event. It is one small moment within a planetary electrical system that stretches from the surface of the Earth to the edge of space, quietly linking thunderstorms across the entire globe. Inside a powerful thunderstorm, far above the ground where the air is thin and temperatures plunge well below freezing, tiny particles of ice begin a remarkable journey. These particles may start as small droplets of water or fragments of ice crystals, barely noticeable within the swirling interior of the cloud, yet under the right conditions they can grow into solid spheres of ice large enough to dent cars, shatter windows, and rattle rooftops with startling force. These frozen projectiles are known as hailstones. Hail is one of the more dramatic outcomes of convective storms, but its formation depends on a surprisingly delicate balance of physical processes taking place inside the cloud. At the center of this process is a combination of powerful rising air currents and an unusual type of water that behaves in ways most people would not expect. That unusual form of water is known as supercooled water. Under everyday conditions, water freezes at 0 degrees Celsius. However, in the atmosphere, droplets of water can remain liquid even when temperatures fall well below that freezing point. When water stays liquid below 0 degrees Celsius, it is described as supercooled. Supercooled droplets are surprisingly common inside thunderstorms. Within the towering columns of rising air, water droplets can remain liquid at temperatures as low as -20 degrees Celsius, or even colder. The reason they do not freeze immediately is that freezing usually requires a surface or particle that allows ice crystals to begin forming. In the absence of such particles, droplets may remain liquid even at temperatures where freezing would normally occur. When supercooled droplets encounter a solid surface, such as an ice particle or a snow crystal, they freeze almost instantly. Inside a thunderstorm cloud, this process begins when small ice crystals form in the upper regions of the cloud where temperatures are extremely low. These ice crystals may originate from frozen droplets or from tiny ice nuclei present in the atmosphere. Once the first ice particles appear, they begin interacting with the surrounding supercooled droplets. The storm's powerful updrafts carry both droplets and ice particles upward through the cloud. As they collide, the supercooled droplets freeze onto the surface of the ice particles, causing them to grow larger. At first, these particles are small and irregular, sometimes forming a type of ice pellet known as graupel. Graupel has a rough, opaque appearance because it forms when droplets freeze rapidly onto snow crystals. But in strong storms with vigorous updrafts, these growing ice particles may be carried upward repeatedly through different layers of the cloud. Each time the particle rises into a region filled with supercooled droplets, additional layers of ice accumulate on its surface. As it grows heavier, gravity begins pulling it downward. Yet before it can fall out of the cloud, the storm's powerful rising currents may lift it back upward once again. This cycle can repeat several times. The result is the gradual formation of a hailstone, built layer by layer through repeated journeys within the storm. Meteorologists sometimes describe this process as recirculation within the updraft. The storm's vertical air currents act almost like a conveyor system, repeatedly lifting and dropping the growing ice particle through zones where supercooled droplets are abundant. With each pass through these regions, another layer of ice forms. Scientists have studied this process carefully using aircraft observations, laboratory experiments, and radar measurements. One of the researchers who contributed significantly to our understanding of hail formation was atmospheric scientist Charles Knight. Knight investigated how hailstones grow and how their structure reveals clues about the environment inside thunderstorms. His research showed that the internal layers of hailstones can act almost like a record of the storm's internal conditions. If you were to slice a hailstone open, you might see alternating layers of clear ice and opaque ice arranged in rings around the center. These layers form under different freezing conditions. Clear ice tends to form when supercooled droplets freeze slowly and smoothly onto the hailstone's surface. During this slower freezing process, trapped air bubbles escape before the ice solidifies, leaving behind a transparent layer. Opaque ice forms when freezing occurs very rapidly. In this case, air bubbles become trapped inside the ice, scattering light and producing a cloudy appearance. The alternating pattern of clear and opaque layers can reveal how the hailstone traveled through different parts of the storm cloud. Each layer represents a stage in its journey through regions of varying temperature, moisture, and updraft strength. In this way, A single hailstone can serve as a miniature archive of the storm that created it. Some hailstones remain relatively small, no larger than a pea. Others grow much larger when the storm's updrafts are especially powerful. In the most intense storms, hailstones can reach diameters of several centimeters. Occasionally they grow even larger, approaching the size of golf balls, tennis balls, or in rare cases even grapefruits. A hailstone weighing several hundred grams may fall from an altitude of several kilometers. By the time it reaches the ground, it can be traveling at speeds exceeding 100 kilometers per hour. It is not surprising that such impacts can cause significant damage. Because hail formation depends on strong updrafts and abundant supercooled water, it tends to occur most often within severe thunderstorms. Regions such as the Central Plains of the United States, sometimes called Hail Alley, experience frequent hail events because the atmospheric conditions there often favor powerful convective storms. Scientists have devoted considerable effort to studying these storms in detail. The National Center for Atmospheric Research, commonly known as NCAR, has conducted extensive research on hail formation and storm dynamics. Using specialized radar systems, research aircraft, and high-resolution computer models, NCAR scientists investigate how storm structure influences hail growth. Their work helps improve weather forecasting and provides better understanding of how severe storms develop. One of the key insights from this research is that hail formation depends strongly on the structure of the storm's updraft. A strong, sustained updraft allows hailstones to remain suspended in the cloud long enough to grow through repeated layers of freezing. If the updraft weakens or shifts position, the hailstone may finally fall to the ground. When that happens, the hailstone's journey through the storm comes to an end. For observers on the ground, hail often arrives suddenly. A storm that moments earlier produced only rain may suddenly begin dropping solid ice from the sky. The sound of hailstones striking rooftops, windows, and pavement can be startling, even a little dramatic. Yet each of those ice pellets has traveled through a complex and fascinating process high inside the storm cloud. From tiny droplets of supercooled water to layered spheres of solid ice, hailstones are shaped by the invisible architecture of rising air and turbulent motion inside thunderstorms. They are small, frozen reminders of the powerful vertical engine operating within convective storms, quietly recording the story of their journey through the storm's hidden interior. Among the many phenomena that emerge from powerful thunderstorms, few capture the imagination quite like tornadoes. These narrow, violently rotating columns of air can appear almost suddenly beneath storm clouds, twisting downward from the sky and carving paths across the landscape. To observers on the ground, they can look almost unreal, like a rope or funnel of cloud reaching toward the earth. Despite their dramatic appearance, tornadoes are not mysterious forces acting outside the laws of physics. They are extreme examples of a phenomenon that occurs frequently in fluids of all kinds. That phenomenon is a vortex. A vortex is simply a rotating flow of fluid around a central axis. The concept may sound technical, but examples are easy to find in everyday life. When water drains from a sink, it forms a spinning whirlpool. Smoke rising from a candle may twist gently into spirals. Even the swirling motion of cream mixing into coffee can reveal small rotating eddies. Tornadoes belong to the same family of rotating flows, but on a much larger and more energetic scale. The physics of vortices has fascinated scientists for centuries. One of the most influential contributors to this field was the German physicist Hermann Helmholtz. In the 19th century, Helmholtz developed a set of principles describing how vortices behave in fluids. Helmholtz demonstrated that vortex motion tends to conserve circulation. In simpler terms, once a region of rotating fluid forms, it tends to persist and maintain its rotation, unless disrupted by outside forces. His work also showed that vortices can stretch, bend, and interact with surrounding flows in complex ways. These ideas apply directly to the atmosphere. Air behaves as a fluid, and when it begins rotating, the motion can concentrate into narrow, intense structures. Tornadoes represent one of the most extreme outcomes of that concentration. To understand how tornadoes form, it helps to start with the larger environment of the thunderstorm that produces them. Not all thunderstorms create tornadoes. In fact, only a small fraction do. Tornado formation usually requires a specific combination of atmospheric ingredients. One of the most important ingredients is wind shear. Wind shear occurs when wind speed or direction changes with altitude. Near the ground, the wind might blow slowly from one direction, While several kilometers higher, the wind may move faster and come from a different direction. This vertical difference in wind creates horizontal tubes of rotating air within the atmosphere. These rotating tubes are not yet tornadoes. They are more like invisible rolls of air spinning sideways. Now imagine a powerful thunderstorm forming in this environment. The storm's updraft begins lifting warm air rapidly upward through the atmosphere. If one of those invisible rotating tubes encounters the updraft, the rising motion can tilt the horizontal rotation into a vertical orientation. At that moment, the rotating air column begins standing upright inside the storm. This process is called vortex tilting. Once the rotation becomes vertical, another important process may occur. As the rotating air is pulled upward into the storm's updraft, the column of air stretches vertically. When a rotating column stretches, the rotation becomes faster. This effect is similar to what happens when a figure skater pulls their arms inward during a spin. As the skater's body becomes more compact, the rate of rotation increases. In fluid dynamics, this behavior is described as vortex stretching. Inside a thunderstorm, vortex stretching can intensify rotation dramatically. When conditions are favorable, the rotating column within the storm grows stronger and more organized. The storm itself may develop a persistent rotating updraft known as a mesocyclone. Mesocyclones are characteristic features of a type of thunderstorm called a supercell. Supercells are among the most powerful and long-lived convective storms on Earth. Within a supercell, the rotating updraft can persist for an hour or more, continuously drawing energy from warm, moist air near the ground. Under certain conditions, the rotation near the base of the storm tightens and intensifies. Eventually, the rotating air column may extend downward toward the ground. When that rotating column reaches the surface, a tornado is born. Tornadoes can vary greatly in size and intensity. Some are narrow funnels only a few tens of meters wide. Others grow to more than a kilometer in diameter. Wind speeds inside the most intense tornadoes can exceed 300 kilometers per hour. The destructive power of these winds is remarkable. Houses can be torn apart, vehicles lifted and thrown, and trees stripped of their branches. Understanding how such powerful storms behave has required careful observation and scientific investigation. One of the researchers who has devoted decades to studying tornadoes in the field is meteorologist Howard Bluestein. Bluestein has conducted numerous field experiments in which teams of scientists deploy specialized instruments near developing storms. Using mobile radar systems, high-speed cameras, and weather sensors, his research group has gathered detailed observations of tornado structure and evolution. These measurements have revealed that tornadoes are far from simple rotating funnels. Inside the broader circulation, there may be multiple smaller vortices spinning around the main core. These smaller vortices can intensify wind speeds locally and contribute to the damage patterns observed on the ground. In some cases, several smaller vortices orbit within the larger tornado circulation, producing complex wind patterns that shift rapidly over short distances. Another scientist whose work profoundly shaped tornado research was Tetsuya Theodore Fujita. Often known simply as Ted Fujita, he was a Japanese-American meteorologist whose curiosity about severe storms transformed the field. In the 1950s and 1960s, Fujita began analyzing the damage left behind by tornadoes. By carefully examining patterns of destruction across affected areas, he developed methods for estimating the strength of tornado winds. His work led to the creation of the Fujita scale, which classifies tornado intensity based on the damage they cause. The scale ranges from weaker tornadoes capable of causing minor damage to the most powerful events capable of leveling entire buildings. Later refinements produced the enhanced Fujita scale, which remains the standard system used today to rate tornado intensity. Fujita's research went far beyond damage surveys. He also studied aerial photographs of storm damage and discovered patterns that revealed hidden structures within tornadoes. His observations helped identify the presence of multiple vortices and other complex flow features within tornado systems. Through this careful detective work, Fujita turned the aftermath of storms into valuable scientific data. Tornadoes remain one of the most challenging weather phenomena to predict with precision. While meteorologists can often identify environments where tornadoes are likely, forecasting the exact location and timing of a tornado remains difficult. The atmosphere's sensitivity to small changes means that slight variations in storm structure can determine whether a rotating storm produces a tornado or simply continues as a powerful thunderstorm. Yet despite these challenges, Research over the past several decades has dramatically improved our understanding of tornado formation. Modern Doppler radar systems can detect rotating air within storms long before a tornado forms. Satellite observations track the larger atmospheric patterns that support severe weather outbreaks. Field experiments continue to reveal new details about the internal structure of rotating storms. Even so, tornadoes remain awe-inspiring examples of the atmosphere's ability to concentrate energy into narrow, intense structures. They are born from the same basic ingredients that produce ordinary storms: warm air, rising motion, and atmospheric instability. Yet when combined with wind shear and vortex dynamics, those ingredients can produce rotating columns of air powerful enough to reshape entire landscapes. Seen through the lens of fluid dynamics, tornadoes are extraordinary demonstrations of vortex physics unfolding in the open sky. They remind us that the atmosphere is not only a system of clouds and winds, but also a vast fluid environment where the principles of motion, rotation, and energy interact in ways that can be both beautiful and formidable. When we experience weather at the surface of the Earth, it often feels local and immediate. A windy afternoon, a passing storm, or a stretch of calm, sunny days can make it seem as though the atmosphere is responding only to nearby conditions. Yet the air surrounding our planet is part of a vast interconnected circulation system that operates across entire hemispheres. From a planetary perspective, the atmosphere behaves like a gigantic conveyor belt that moves heat from warmer regions toward cooler ones. Without this circulation, the equator would continue absorbing large amounts of solar energy, while the polar regions remained extremely cold. Over time, the temperature differences would become far more extreme than anything we experience today. The atmosphere prevents that imbalance by constantly transporting energy around the globe. One of the key ideas that helps scientists understand this movement is the concept of large-scale atmospheric circulation cells. These circulation patterns divide the atmosphere into several broad regions where air rises, travels horizontally, sinks, and then returns toward its starting point. The first of these patterns is known as the Hadley cell. The Hadley cell operates in tropical regions between the equator and roughly 30 degrees latitude. Near the equator, the surface of the Earth receives the most intense sunlight. This strong heating warms the air close to the ground, causing it to rise through convection. As the air rises, it cools and releases moisture, often forming towering clouds and frequent tropical rainfall. The region where this rising motion occurs is known as the Intertropical Convergence Zone, a band of stormy weather that circles the globe near the equator. Once the air reaches higher altitudes in the troposphere, it spreads outward toward the north and south. As it travels away from the equator, the air gradually cools and eventually begins to sink around 30 degrees latitude. This sinking air creates regions of relatively high atmospheric pressure. Many of the world's deserts lie beneath these descending air masses, including the Sahara Desert and the deserts of Australia. After descending, the air flows back toward the equator near the surface, completing the loop of the Hadley circulation. The second circulation pattern is called the Ferrel cell. This cell occupies the middle latitudes between roughly 30 and 60 degrees latitude in both hemispheres. Unlike the Hadley cell, which is driven directly by tropical heating, the Ferrel cell emerges as a result of interactions between neighbouring circulation systems. Within the Ferrel cell, surface winds generally move from west to east. These winds are commonly known as the prevailing westerlies. They play an important role in steering weather systems across continents and oceans. Farther toward the poles lies the polar cell. In these regions, cold, dense air near the poles tends to sink toward the surface and spread outward. As this air moves toward lower latitudes, it eventually rises again where it meets warmer air masses. Together, the Hadley, Ferrel, and polar cells form a three-cell circulation pattern in each hemisphere. These patterns help organize the large-scale movement of air around the planet. However, the situation becomes more complex because the Earth itself is rotating. As air moves across the rotating surface of the planet, its path does not remain straight. Instead, it appears to curve relative to the surface. This deflection is known as the Coriolis effect. The Coriolis effect was described mathematically by the French engineer and mathematician Gaspard Gustave de Coriolis during the 19th century. Coriolis was studying the motion of objects within rotating systems such as spinning machinery. His equations reveal that objects moving across a rotating surface experience an apparent sideways force. On Earth, this effect causes moving air to curve to the right in the northern hemisphere and to the left in the southern hemisphere. The Coriolis effect does not actually push the air sideways in the way a physical force might. Instead, it arises because the Earth's surface rotates beneath moving air. The result is that winds follow curved paths rather than straight lines. This deflection plays a crucial role in shaping global wind systems. For example, air flowing from the subtropics toward the equator within the Hadley cell does not travel directly southward or northward. Instead, it curves westward as it moves, creating the trade winds that once powered sailing ships across the oceans. Similarly, the prevailing westerlies of the mid-latitudes arise because air flowing toward the poles is deflected eastward by the rotation of the planet. The interplay between pressure differences and the Coriolis effect produces a complex pattern of winds across the globe. Yet even this description captures only part of the atmosphere's behaviour. The large-scale circulation cells themselves are influenced by another phenomenon known as Rossby waves. Rossby waves were first described by meteorologist Carl Gustav Rossby in the 1930s. Rossby recognised that the atmosphere behaves like a fluid flowing over a rotating sphere. Under these conditions, large-scale waves can develop in the flow of air. These waves appear as broad north-south meanders in the high-altitude wind currents known as the jet streams. The jet streams are fast-moving rivers of air located near the boundary between the troposphere and the stratosphere. Wind speeds in these currents can exceed 200 km per hour. Rossby waves cause the jet streams to undulate across the planet rather than flowing in perfectly straight lines. These undulations influence the movement of weather systems. When the jet stream dips southward in a large wave, it can draw cold polar air toward lower latitudes. When it bends northward, warm tropical air may move toward the poles. This shifting pattern helps explain why weather conditions in many regions can change rapidly, from warm to cold or from calm to stormy. Another important factor shaping global winds is the conservation of angular momentum. Angular momentum describes the rotational motion of objects moving around an axis. On a rotating planet like Earth, air moving toward or away from the axis of rotation must adjust its speed in order to conserve angular momentum. An everyday example can help illustrate this idea. When a spinning figure skater pulls their arms inward, their rotation speeds up. When they extend their arms outward, the rotation slows down. A similar effect occurs in the atmosphere. Air moving toward the poles is moving closer to the axis of Earth's rotation. To conserve angular momentum, the air accelerates eastward, strengthening the high-altitude winds of the jet streams. This process contributes to the powerful west to east winds observed in the upper atmosphere. Although these global circulation patterns operate on enormous scales, they have direct consequences for the weather experienced in individual regions. The position of the jet streams influences where storms develop and how they move across continents. Shifts in the Hadley circulation can alter rainfall patterns in tropical regions. Variations in Rossby wave patterns can lead to extended periods of warm or cold weather. In this way, the winds that shape local weather are ultimately connected to planetary scale movements of air. What may feel like a simple breeze passing through a city park or across an open field is often part of a much larger atmospheric journey. The air flowing past you may have travelled thousands of kilometres, guided by pressure gradients, curved by the rotation of the Earth, and shaped by the vast circulation patterns that link the tropics, mid-latitudes, and polar regions. The atmosphere is therefore not a collection of isolated weather events, but a single interconnected system. Every gust of wind, every storm front, and every drifting cloud is influenced by the continuous motion of air around the planet. If you could zoom in on the lowest portion of the atmosphere, the layer closest to the ground where we live and breathe, you would find a region where the air behaves very differently from the sky above it. This zone is known as the planetary boundary layer. The planetary boundary layer is the portion of the atmosphere that directly interacts with the surface of the Earth. Its depth varies throughout the day, sometimes only a few hundred meters thick during calm nights, and at other times extending 1 or even 2 kilometers upward when daytime heating causes strong mixing. Within this layer, the air is constantly responding to the presence of the surface below it. The land heats during the day and cools at night. Oceans release stored heat slowly. Forests release moisture through transpiration. Cities warm the air with buildings, pavement, and human activity. All of these influences shape the behavior of the air in the boundary layer. Unlike the smoother flow of winds higher in the atmosphere, the boundary layer is filled with turbulence and friction. When wind moves across the Earth's surface, it encounters obstacles such as trees, buildings, hills, and uneven terrain. These obstacles slow the air near the ground and create swirling motions that mix the lower atmosphere. The result is a region of constant interaction between the atmosphere and the planet itself. Because friction slows the wind near the surface, the direction and speed of winds change with altitude. Meteorologists describe this gradual turning of the wind using a concept known as the Ekman spiral. The Ekman spiral was first described by the Swedish oceanographer Vagn Wolfrid Ekman in the early 20th century. Ekman was studying how wind affected ocean currents, but his work revealed a principle that applies equally well to the atmosphere. Ekman realized that when wind blows across a rotating planet, friction at the surface slows the motion of the air near the ground. Because the Coriolis effect continues to act on the moving air, the balance between pressure forces and rotational deflection changes with height. As a result, the direction of the wind gradually rotates as altitude increases. Near the surface, friction keeps the wind from fully balancing the pressure gradient force and the Coriolis effect. The wind therefore flows slightly across lines of equal pressure rather than exactly along them. A few hundred meters above the ground, where friction becomes weaker, the wind turns more strongly under the influence of the Coriolis effect. The combined result is a spiral pattern in the wind direction, with increasing altitude known as the Ekman spiral. Although this turning motion is subtle, it plays an important role in transporting heat, moisture, and pollutants within the boundary layer. Another feature that strongly influences conditions near the ground is the temperature structure of the air. Under typical daytime conditions, the atmosphere cools gradually with height. Warm air near the surface rises and mixes with cooler air above, creating vertical motion that keeps the boundary layer relatively well mixed. However, under certain circumstances, the normal pattern reverses. Sometimes a layer of warm air settles above cooler air near the ground. When this occurs, the atmosphere develops what meteorologists call a temperature inversion. A temperature inversion acts like a lid on the atmosphere. Because the warm air above is lighter and more stable, it prevents the cooler air below from rising and mixing upward. Inversions commonly form during calm nights, when the ground loses heat through radiation. As the surface cools, the air directly above it also cools. If the wind is weak, this cool air remains trapped near the ground while slightly warmer air persists above it. This stable layering can lead to several noticeable effects. One of the most familiar is the formation of fog. Fog forms when air near the ground becomes saturated with moisture, and water vapor condenses into tiny droplets suspended in the air. When an inversion traps cool, moist air close to the surface, the conditions become ideal for fog development. Radiation fog often forms during clear nights when the ground cools rapidly after sunset. As the temperature drops toward the dew point, water vapor condenses into a thin layer of cloud hugging the surface. In coastal regions, another type called advection fog can occur when warm, moist air moves over cooler ocean waters. The cooling causes condensation, creating dense fog banks that drift inland. Fog is essentially a cloud that forms at ground level, yet its behavior is strongly controlled by the delicate balance of temperature, moisture, and wind within the boundary layer. Because the boundary layer is directly influenced by the Earth's surface, local geography can also shape weather in fascinating ways. Mountains can redirect winds and force air upward, creating clouds and precipitation on one side, while leaving dry conditions on the other. Valleys can trap cool air during the night, leading to frequent fog formation. Large bodies of water such as oceans and lakes influence nearby climates by absorbing and releasing heat slowly. Coastal regions often experience milder temperatures because water moderates the heating and cooling of the surrounding air. Vegetation also plays an important role. Forests release water vapor through a process called transpiration, adding moisture to the air above them. Fields of crops, wetlands, and even city parks contribute to the local balance of heat and humidity. Cities themselves create distinctive microclimates. Concrete, asphalt, and buildings absorb large amounts of solar radiation during the day and release that heat slowly at night. This process produces what meteorologists call the urban heat island effect, where temperatures in cities remain several degrees warmer than surrounding rural areas. These local influences demonstrate that weather does not depend solely on large-scale atmospheric patterns. The immediate environment near the surface can shape the air in subtle but important ways. Understanding the boundary layer has therefore become an important focus of atmospheric science. Researchers such as John Wingard have spent decades studying turbulence and energy exchange in the boundary layer. Wingard's work has helped scientists understand how heat, moisture and momentum move between the Earth's surface and the atmosphere above. His research has contributed to improved weather forecasting, better climate models, and a deeper understanding of how the atmosphere interacts with landscapes. The boundary layer may be the thinnest part of the atmosphere, but it is also the most intimately connected to the world we experience every day. It is where breezes rustle through trees, where fog rolls quietly across fields, and where the warmth of the ground shapes the air we breathe. In this narrow zone between Earth and sky, the atmosphere constantly responds to the surface below it, forming a delicate interface where global circulation meets the fine details of local landscapes. Across the warm waters of the tropical oceans, the atmosphere occasionally organizes itself into one of the most powerful and elegant systems found in nature. At first, it may appear as little more than a cluster of thunderstorms drifting slowly across the sea, but under the right conditions, that cluster can evolve into something far larger and far more organized. It becomes a tropical cyclone. Tropical cyclones are among the most energetic weather systems on Earth. In different regions, they are known by different names. In the Atlantic and Eastern Pacific, they are called hurricanes. In the Western Pacific, they are known as typhoons. In the Indian Ocean and parts of the Southern Hemisphere, they are simply referred to as cyclones. Despite the different names, the underlying physics is the same. A tropical cyclone functions as a massive atmospheric heat engine. Its energy source is not fuel in the usual sense, but the warm water of the tropical ocean. When ocean temperatures reach roughly 26 to 27 degrees Celsius or higher, the surface water begins releasing large amounts of heat and moisture into the air above it. This heat transfer occurs primarily through evaporation. Water molecules escape from the ocean surface and enter the atmosphere as water vapor. Warm, moist air rises from the ocean surface through convection. As it rises and cools, the water vapor condenses into clouds and rain. During condensation, latent heat is released into the surrounding air. This release of latent heat warms the air within the storm, making it more buoyant than the surrounding atmosphere. As a result, the air continues to rise even more vigorously. The process creates a feedback loop. Rising air lowers the surface pressure beneath the storm. Lower pressure allows more warm air from the surrounding ocean to flow inward toward the center. As this air converges and rises, more condensation occurs, releasing more latent heat. The storm begins organizing itself into a rotating system. Because the Earth rotates, the Coriolis effect causes the inflowing air to curve. Instead of rushing directly toward the center, the winds spiral inward. This rotation is essential for the development of a tropical cyclone. Without planetary rotation, the system would not organize into a spinning storm. As the storm intensifies, its structure becomes more defined. At the center lies a region known as the eye. The eye of a hurricane is often surprisingly calm. Winds weaken, and the skies may even clear temporarily. This calm region typically measures between 20 and 50 kilometers across, although some storms produce eyes both smaller and larger. Surrounding the eye is the eye wall, the most intense part of the storm. The eye wall contains towering clouds where the strongest winds and heaviest rainfall occur. In powerful hurricanes, wind speeds in the eye wall can exceed 200 kilometers per hour. Outside the eye wall, bands of thunderstorms spiral outward in long, curved arcs known as rain bands. These rain bands may stretch hundreds of kilometers from the center of the storm and can produce heavy rain, gusty winds, and occasional tornadoes. The entire storm system may span several hundred kilometers across. Viewed from space, a mature hurricane often resembles a vast swirling pinwheel of clouds rotating across the ocean. Meteorologists have developed ways to categorize these storms based on their wind speeds. One widely used classification system is the Saffir-Simpson Hurricane Wind Scale. This scale was developed during the 1970s by engineer Herbert Saffir and meteorologist Robert Simpson. Herbert Saffir initially created the scale as a method for estimating potential structural damage caused by hurricane winds. Robert Simpson, who served as director of the National Hurricane Center, later refined the scale to include additional meteorological information. The Saffir-Simpson scale divides hurricanes into 5 categories based on sustained wind speed. Category 1. Hurricanes produce winds beginning around 119 kilometers per hour. Category 5 storms, the most powerful classification, have winds exceeding 250 kilometers per hour. While wind speed is a major factor in determining a hurricane's category, it is not the only source of danger. Heavy rainfall, storm surge, and flooding often cause the greatest damage. Storm surge occurs when powerful winds push ocean water toward the coastline. In severe hurricanes, this surge of seawater can raise water levels several meters above normal tide levels, flooding coastal regions. The strength a hurricane can ultimately reach depends strongly on the energy available from the ocean below. Meteorologist Kerry Emanuel developed a framework known as potential intensity theory to describe the upper limits of hurricane strength. According to Emanuel's theory, a hurricane's maximum intensity depends on the difference between the temperature of the warm ocean surface and the colder temperatures found higher in the atmosphere. The greater this temperature difference, the more energy the storm can potentially extract from the ocean. In simple terms, a hurricane behaves somewhat like a heat engine operating between a warm reservoir and a cold reservoir. The warm reservoir is the ocean surface. The cold reservoir is the upper atmosphere. As long as warm water continues feeding the storm and atmospheric conditions remain favorable, the hurricane can continue intensifying. However, several factors can limit a storm's growth. One limiting factor is wind shear. If winds at different altitudes move at very different speeds or directions, the storm's structure can become disrupted. Strong wind shear can tilt the storm's circulation and prevent it from organizing efficiently. Another factor is the availability of ocean heat. Ocean heat content refers not only to the temperature at the surface, but also to how deep the warm water extends. If warm water exists only in a thin surface layer, the storm may churn up colder water from below, weakening its energy supply. But when warm water extends deep into the ocean, the storm can continue drawing energy without quickly cooling the surface. Climate variability also influences where and when tropical cyclones form. Large-scale patterns such as the El Niño Southern Oscillation affect sea surface temperatures and atmospheric wind patterns across the Pacific Ocean. During certain phases of these climate cycles, conditions become more favorable for cyclone development in some regions and less favorable in others. Scientists study these patterns carefully to understand long-term trends in hurricane activity. Research aircraft operated by organizations such as the National Oceanic and Atmospheric Administration often fly directly into developing hurricanes to collect measurements. These aircraft release instruments known as dropsondes that measure temperature, humidity, pressure, and wind speed as they fall through the storm. Satellite observations also provide continuous monitoring of storm development across the oceans. Together, these observations help meteorologists track storms and improve forecasts that can provide advance warning to coastal communities. Yet even with modern technology, hurricanes remain awe-inspiring demonstrations of atmospheric physics. Each storm represents a vast exchange of energy between the ocean and the atmosphere. Heat stored in tropical waters becomes clouds, wind, rain, and towering spirals of motion visible from space. At their peak, hurricanes can release energy equivalent to many thousands of times the electrical power generated by human civilization. And all of that energy ultimately traces back to sunlight warming the surface of the ocean. From the quiet evaporation of water molecules to the roaring winds of a mature cyclone, the entire system is part of a continuous process by which the atmosphere redistributes heat across the planet. In that sense, hurricanes are not just storms, they're enormous rotating engines in the sky, driven by the simple but powerful exchange of heat between the ocean and the air above it. Far above the clouds where commercial aircraft travel, the atmosphere contains powerful rivers of wind that circle the planet. These currents are invisible from the ground, yet they exert enormous influence over weather systems, temperature patterns, and even the routes taken by long-distance flights. These high-altitude wind currents are known as jet streams. Jet streams are narrow bands of extremely fast-moving air that form near the boundary between the troposphere and the stratosphere. This boundary region is called the tropopause. At these heights, which typically range between 8 and 12 kilometers above the surface depending on latitude, the atmosphere undergoes a sharp transition in temperature structure. Within the troposphere, temperature generally decreases with altitude. Above the tropopause in the stratosphere, the pattern reverses and temperature begins to increase with height, due to the absorption of ultraviolet radiation by ozone. The tropopause therefore acts as a kind of atmospheric boundary separating two very different thermal environments. Along this boundary, strong temperature contrasts often develop between air masses originating in the tropics and those arriving from polar regions. Whenever strong temperature differences exist across horizontal distances, powerful winds tend to form. This is a direct consequence of pressure gradients within the atmosphere. Jet streams emerge from these pressure gradients. They appear as narrow corridors where winds accelerate dramatically, sometimes exceeding 200 km per hour. In especially intense situations, wind speeds may approach 300 km per hour. Although jet streams circle the planet, they are not perfectly straight or uniform. Instead, they twist and bend across continents and oceans, forming sweeping arcs that guide the movement of weather systems below. The discovery of these powerful winds has an interesting history. In the early 1900s, a Japanese meteorologist named Wasaburo Oishi began launching weather balloons from a mountain observatory near Mount Fuji. Oishi carefully tracked the movement of the balloons as they ascended into the upper atmosphere. By analysing their trajectories, he noticed that winds at high altitudes often moved extremely quickly from west to east. His observations revealed the presence of strong upper-level winds long before the era of satellites or jet aircraft. Unfortunately, much of Oishi's work was published in Esperanto, a language intended to be internationally accessible but rarely used in scientific communication at the time. As a result, his discoveries remained largely unnoticed outside Japan for many years. Only later did other scientists confirm the existence of these powerful winds, which came to be known as jet streams. Understanding why jet streams form requires examining the dynamics of air masses with different temperatures. When warm tropical air meets colder polar air, the boundary between them becomes a region of strong horizontal temperature gradients. These gradients create what meteorologists call baroclinic conditions. Baroclinic instability occurs when differences in temperature and density across horizontal distances allow atmospheric waves to grow and amplify. This concept was studied extensively by meteorologist Jules Charny during the mid-20th century. Charny developed mathematical models that showed how small disturbances in the atmosphere could grow into large-scale wave patterns under baroclinic conditions. These growing waves play a key role in generating mid-latitude weather systems. Within the jet stream, these waves appear as broad north-south undulations that sweep across the globe. Meteorologists often call them Rossby waves, after the scientist Carl Gustav Rossby, who studied their properties. These waves shape the paths taken by storms. When the jet stream bends southward in a large wave, colder air from higher latitudes can spill toward warmer regions. When it curves northward, warm air can travel toward the poles. The shifting pattern of these waves helps explain why weather in many regions can change quickly. A deep southward dip in the jet stream may bring a sudden cold spell. A northward bulge can produce unusual warmth. The jet stream therefore acts like a steering current for weather systems. Low-pressure systems and storm fronts tend to follow the flow of the jet stream. When the jet stream moves rapidly across the continent, storms may pass quickly from west to east. When the jet stream slows or becomes blocked in a large wave pattern, weather systems may linger in one region for extended periods. These persistent patterns can lead to prolonged heat waves, cold spells, or heavy rainfall. Another important principle governing the behavior of the jet stream is the conservation of potential vorticity. Potential vorticity combines several physical properties of the atmosphere, including rotation, stratification, and fluid motion. Although the mathematics behind potential vorticity can be complex, the basic idea is that rotating air parcels tend to conserve certain aspects of their motion as they move through the atmosphere. When air flows over mountains or moves between regions of different temperature, its rotation and vertical structure adjust in ways that preserve this conserved quantity. This conservation helps maintain the wave-like structure of the jet stream and contributes to the development of large-scale atmospheric patterns. Potential vorticity conservation also helps meteorologists understand why certain disturbances in the atmosphere can grow rapidly into storms. When upper-level air with high potential vorticity moves over warmer lower-level air, it can destabilize the atmosphere and encourage rising motion. This interaction often leads to the development of mid-latitude cyclones, the large rotating storm systems that bring rain, snow, and strong winds to many parts of the world. Although jet streams exist primarily at high altitudes, their influence extends all the way down to the surface. They help guide the movement of storm systems, shape temperature patterns across continents, and influence the formation of high and low pressure systems. For aircraft travelling across the oceans, jet streams can have practical consequences as well. Flights travelling eastward often take advantage of strong tailwinds within the jet stream to reduce travel time. Flights moving in the opposite direction may follow more southerly routes to avoid the strongest headwinds. Even migratory birds sometimes benefit from these high-altitude winds. From a planetary perspective, jet streams represent another mechanism by which the atmosphere redistributes energy. They form along the boundaries between contrasting air masses and help transport momentum and heat across large distances. The invisible rivers of wind flowing near the tropopause connect distant regions of the planet, guiding storms and shaping the rhythm of weather. Though we rarely see them directly, their presence can be felt in the changing skies below, as storm systems follow the pathways carved through the upper atmosphere by these powerful currents of air. On certain nights in the far northern and southern reaches of our planet, the sky performs a quiet and astonishing display of light. Curtains of green shimmer across the darkness. Pale arcs ripple gently from horizon to horizon. Occasionally streaks of red or violet glow above the landscape, shifting slowly as if the sky itself were breathing. These luminous displays are known as auroras. In the northern hemisphere they are called the aurora borealis, or northern lights. In the southern hemisphere they are known as the aurora australis. Although they appear delicate and almost dreamlike, auroras are the visible result of powerful physical processes that connect the Earth directly to the Sun. To understand how auroras form, it helps to begin far beyond the atmosphere. The Sun constantly releases a stream of charged particles into space. This flow of particles is called the solar wind. The solar wind consists mostly of electrons and protons moving outward from the Sun at speeds that can exceed several hundred kilometers per second. Under normal conditions, the solar wind spreads across the entire solar system. If Earth had no protective magnetic field, these energetic particles would stream directly into the atmosphere and gradually strip it away, much as they have done on planets like Mars. Fortunately, our planet is surrounded by a powerful magnetic field generated deep within its molten outer core. This magnetic field forms a protective region in space known as the magnetosphere. The magnetosphere acts like an invisible shield. As the solar wind approaches Earth, most of the charged particles are deflected around the planet by the magnetic field. However, the interaction between the solar wind and the magnetosphere is not perfectly smooth. Some particles become trapped along magnetic field lines that extend from the poles of the planet out into space. These magnetic field lines guide the particles toward the upper atmosphere near the polar regions. When the particles finally collide with gases in the upper atmosphere, the aurora is born. The collisions occur primarily in a region called the ionosphere, located roughly 80 to 500 kilometers above the surface. In this region, the atmosphere is extremely thin, but it still contains atoms and molecules of oxygen and nitrogen. When energetic electrons from the solar wind collide with these atoms, they transfer energy to them. The excited atoms briefly hold that energy before releasing it as light. Different atmospheric gases produce different colors. Oxygen atoms often produce the green glow most commonly seen in auroras. Under certain conditions, oxygen can also emit a deep red light at higher altitudes. Nitrogen molecules contribute shades of blue, violet, and occasionally pink along the edges of auroral curtains. The exact colors depend on altitude, atmospheric composition, and the energy of the incoming particles. Although auroras appear gentle and quiet from the ground, the electrical processes behind them are surprisingly powerful. One of the scientists who helped explain these processes was the Norwegian physicist Christian Birkeland. In the early 1900s, Birkeland conducted experiments using magnetized spheres to simulate how charged particles from the Sun might interact with Earth's magnetic field. His laboratory device, known as a terrella, allowed him to recreate miniature auroral patterns around a small magnetic globe. From these experiments, Birkeland proposed that electrical currents flowed along Earth's magnetic field lines between space and the atmosphere. These currents would guide charged particles toward the polar regions, where they would produce auroras. At the time, Birkeland's ideas were considered controversial. The technology needed to observe such currents directly did not yet exist. Decades later, satellite measurements confirmed that Birkeland's theory was correct. The currents he predicted are now known as Birkeland currents. These are enormous electrical currents flowing along magnetic field lines that connect Earth's magnetosphere to the ionosphere. Each Birkeland current can carry millions of amperes of electrical current, linking the environment of near-Earth space with the upper atmosphere. These currents are part of a larger system of electrical and magnetic interactions, collectively referred to as space weather. Space weather describes the changing conditions in space caused by activity on the Sun. Solar flares, coronal mass ejections, and variations in the solar wind can all disturb Earth's magnetosphere. When strong bursts of solar particles arrive at Earth, the magnetosphere compresses and the flow of charged particles into the polar atmosphere intensifies. During these geomagnetic storms, auroras can become especially bright and widespread. Observers at lower latitudes may occasionally glimpse the glow of auroras during particularly strong events. Historical records describe spectacular auroral displays seen far from the polar regions during powerful solar storms. Modern scientists monitor these events using satellites and space-based instruments. One group of spacecraft studying these interactions is the European Space Agency's Cluster mission. The Cluster mission consists of 4 satellites flying in formation around Earth. By measuring magnetic fields and charged particles in different locations simultaneously, the satellites help scientists understand how energy flows through the magnetosphere. NASA also operates several missions dedicated to studying space weather and auroral processes. Satellites observe the sun's activity, track solar wind conditions, and monitor how these disturbances interact with Earth's magnetic environment. Together, these observations reveal that auroras are not isolated events confined to the atmosphere. They are part of a vast electrical connection linking our planet to the sun. When the solar wind interacts with the magnetosphere, enormous amounts of energy can be transferred into Earth's upper atmosphere. Some of this energy drives the motion of charged particles along magnetic field lines, producing the glowing curtains of the aurora. Other portions of the energy influence the behavior of the ionosphere, affecting radio communication, satellite operations, and even electrical power systems on the ground. The delicate glow of an aurora therefore represents the visible edge of a much larger system. High above the clouds, streams of particles race along invisible magnetic pathways. Electrical currents flow between space and atmosphere. Atoms in the thin upper air briefly absorb energy and release it again as shimmering light. Seen from the ground, the aurora appears calm and almost magical. Yet, it is also a reminder that our atmosphere does not end where the air becomes thin. The Earth is connected to its cosmic surroundings through fields of magnetism and flows of charged particles that extend far beyond the sky we see. When the northern or southern lights ripple silently across the darkness, they reveal that connection in one of the most beautiful ways our planet has to offer. If you step outside on a clear day and look up at the sky, one of the first things you notice is its colour. The sky's blue, sometimes deep and rich, sometimes pale and soft depending on the conditions of the atmosphere. It is such a familiar sight that it rarely invites much curiosity. Yet that colour is the result of a subtle interaction between sunlight and the molecules of air surrounding our planet. Sunlight may appear white, but it is actually a mixture of many different wavelengths of light. Each wavelength corresponds to a different colour, ranging from the longer red wavelengths to the shorter blue and violet wavelengths. When sunlight enters Earth's atmosphere, it encounters billions upon billions of tiny molecules of nitrogen and oxygen. These molecules are far smaller than the wavelengths of visible light, and their interaction with light produces a process known as Rayleigh scattering. Rayleigh scattering was described mathematically in the 19th century by the British physicist John William Strutt, better known as Lord Rayleigh. He demonstrated that very small particles scatter shorter wavelengths of light much more efficiently than longer wavelengths. In practical terms, this means that blue and violet light are scattered more strongly than red light when sunlight passes through the atmosphere. Because blue wavelengths are scattered in all directions by air molecules, the sky appears blue from nearly every angle we look. Some violet light is scattered as well, but the human eye is more sensitive to blue light, and some violet wavelengths are absorbed by the upper atmosphere. The result is the familiar blue dome that stretches above us during the daytime. Rayleigh scattering also explains why sunsets often glow with warm reds and oranges. When the sun sits low on the horizon, sunlight must travel through a much thicker layer of atmosphere before reaching our eyes. During this longer journey, most of the shorter blue wavelengths are scattered away. The remaining light reaching the observer is dominated by longer wavelengths, producing the deep red and orange colours of sunset. While Rayleigh scattering explains the colour of the sky itself, many other atmospheric optical phenomena arise when sunlight interacts with particles that are larger than individual gas molecules. These interactions are described by a different scattering process known as Mie scattering. Mie scattering was developed in the early 20th century by the German physicist Gustav Mie. His work provided a detailed mathematical description of how light interacts with particles, roughly the same size as the wavelength of light. In the atmosphere, such particles include water droplets, dust, smoke, and tiny ice crystals. Unlike Rayleigh scattering, which strongly favours shorter wavelengths, Mie scattering affects a broad range of wavelengths more evenly. This type of scattering is responsible for the white appearance of clouds, where countless droplets scatter sunlight in many directions. Mie scattering also contributes to the hazy appearance of humid or polluted air. When the atmosphere contains many small particles, sunlight is scattered diffusely, reducing visibility and softening the brightness of the sky. Beyond these general scattering effects, the atmosphere can produce a remarkable variety of optical displays when sunlight interacts with water droplets or ice crystals in specific ways. One of the most familiar examples is the rainbow. Rainbows appear when sunlight passes through raindrops suspended in the air. As light enters a droplet, it bends due to refraction. The light then reflects off the inner surface of the droplet before exiting again. During this process, different wavelengths of light are bent by slightly different amounts. This separation of colours is known as dispersion. The result is a circular arc of colour arranged in the familiar sequence from red to violet. The basic explanation for rainbows was first described in detail during the 17th century by the French philosopher and mathematician René Descartes. Descartes used geometric analysis to show how light rays passing through spherical droplets would produce the angles associated with rainbow arcs. Later, Isaac Newton expanded upon this understanding by demonstrating that white light is composed of multiple colours that can be separated by refraction. Newton's experiments with prisms helped establish the modern understanding of the spectrum of visible light. Although rainbows are beautiful and widely known, they're only one example of atmospheric optics. In colder regions of the atmosphere, tiny ice crystals suspended in high-altitude clouds can create another set of optical phenomena known as halos. Halos occur when sunlight passes through hexagonal ice crystals in cirrus clouds. These crystals act like tiny prisms, bending and reflecting light at specific angles. One common halo appears as a faint circular ring surrounding the sun or moon at an angle of about 22 degrees. This phenomenon is known as the 22-degree halo. Another related phenomenon is the sundog, sometimes called a perihelion. Sundogs appear as bright spots of light located on either side of the sun, often accompanied by faint rainbow colours. They form when sunlight passes through flat hexagonal ice crystals that are oriented horizontally as they fall through the atmosphere. These crystals refract light in specific directions, concentrating brightness into small regions of the sky. When conditions are right, sundogs can appear alongside halos and arcs, producing complex patterns of light surrounding the sun. Although these displays may seem rare, they occur more often than many people realise. Thin cirrus clouds containing ice crystals are common in the upper atmosphere, especially ahead of approaching weather systems. One scientist who has devoted much of his career to studying these phenomena is atmospheric optics specialist Walter Tape. Tape's research has helped catalogue and explain many varieties of halo displays produced by ice crystals in the atmosphere. Through careful observation and optical modelling, scientists like Tape have shown that subtle differences in crystal shape and orientation can produce a wide range of halos, arcs, and luminous patterns. Some halo displays are simple and faint, while others can form intricate patterns stretching across large portions of the sky. What all of these phenomena share is a common origin in the interaction between sunlight and the small particles suspended within the atmosphere. Whether it is a molecule scattering blue light across the sky, a raindrop bending sunlight into a rainbow, or an ice crystal refracting light into a halo, the atmosphere acts as an enormous optical laboratory. Every day, sunlight enters this laboratory and encounters an ever-changing mixture of gases, droplets, and crystals. The result is a sky filled with subtle displays of colour and light, quietly revealing the hidden physics of the air that surrounds our world. For most of human history, people believed they had seen nearly everything the sky had to offer. Storms, clouds, lightning, rainbows, and auroras had all been described and studied for centuries. By the middle of the 20th century, meteorology had grown into a sophisticated scientific discipline, with weather balloons, radar systems, and satellites monitoring the atmosphere. Yet even with all that knowledge, the sky still held surprises. Some of the most unusual atmospheric phenomena were discovered only recently, and in some cases almost by accident. These events are rare, fleeting, and often invisible from the ground unless conditions are exactly right. Among the most mysterious is something called ball lightning. Ball lightning has been reported for centuries in eyewitness accounts. Observers have described glowing spheres of light drifting slowly through the air, sometimes appearing during thunderstorms and occasionally even entering buildings through windows or chimneys. These luminous balls are typically described as ranging in size from a few centimeters to perhaps half a meter across. They may glow orange, white, or bluish in color, and sometimes persist for several seconds before fading or disappearing suddenly. Because ball lightning is so rare and unpredictable, scientists struggled for many years to determine whether it was a real physical phenomenon or simply a collection of unusual observations. In recent decades, a few carefully documented cases and laboratory experiments have suggested possible explanations. Some researchers believe ball lightning may involve plasma, a state of matter consisting of electrically charged particles. Others propose that it may form from vaporized silicon compounds produced when lightning strikes soil. Despite these ideas, ball lightning remains one of the least understood electrical phenomena in the atmosphere. While ball lightning occurs near the ground, another group of mysterious events takes place far above thunderstorms. These phenomena are known as transient luminous events. Transient luminous events occur in the upper atmosphere above powerful thunderstorms, often at altitudes far higher than ordinary lightning. They were unknown to science until the late 20th century, largely because they are extremely brief and difficult to observe. The first clear photographic evidence of one such event was captured in 1989 by physicist John R. Winkler and his colleagues at the University of Minnesota. While testing low-light cameras designed to observe distant storms, the team unexpectedly recorded a strange flash of red light above a thunderstorm cloud. The flash lasted only a few milliseconds but appeared far above the storm, reaching into the upper atmosphere. This discovery revealed an entirely new category of atmospheric electrical phenomena. The particular type of flash recorded by Winkler's team became known as a sprite. Sprites are large, faint flashes of red light that appear above thunderstorms at altitudes ranging from about 50 to 90 kilometers. These events occur in the mesosphere, a region of the atmosphere that lies far above the troposphere where ordinary weather takes place. Sprites often appear as branching structures that resemble jellyfish, or delicate tendrils of light spreading downward from the upper atmosphere. Although they're triggered by lightning in the thunderstorm below, sprites occur much higher in the atmosphere where the air is extremely thin. Closely related phenomena include blue jets and elves. Blue jets are narrow cones of blue light that shoot upward from the tops of thunderstorms into the lower regions of the mesosphere. Unlike sprites, which appear above the storm after a lightning discharge, blue jets originate within the thundercloud itself and propagate upward. They can extend as high as 40 or 50 kilometers above the cloud tops. Another phenomenon, known by the unusual acronym ELVES, occurs even higher in the atmosphere. The term ELVES stands for emissions of light and very low-frequency perturbations due to electromagnetic pulse sources. ELVES appear as rapidly expanding rings of light that occur when electromagnetic pulses from lightning strikes interact with the ionosphere. These rings can expand to hundreds of kilometers in diameter, but last for only a fraction of a second. Because these events are so brief and occur high above the clouds, they remained hidden from scientists for many years. Modern technology has changed that. Sensitive cameras, high-speed detectors, and satellite instruments now allow researchers to observe these phenomena in remarkable detail. One important instrument used to study transient luminous events was the imager of sprites and upper atmospheric lightning, often abbreviated as ISUL. This instrument was carried aboard the Taiwanese satellite Formosat 2. The ISUAL instrument operated in orbit for many years, capturing thousands of images of sprites, blue jets, and related phenomena. These observations helped scientists map where and when these events occur around the globe. The data revealed that transient luminous events are not isolated curiosities. They are relatively common above large thunderstorms, particularly in regions where powerful lightning activity occurs. By studying these events, scientists are learning more about the electrical connections between thunderstorms and the upper atmosphere. Lightning does not simply discharge energy downward toward the ground. In some cases, it also sends energy upward, triggering electrical processes in regions of the atmosphere that were once thought to be largely disconnected from ordinary weather. These discoveries remind us that the atmosphere extends far beyond the clouds we see from the ground. Above the familiar storms and winds of the troposphere lies a vast and complex environment where electrical, chemical, and magnetic processes interact. Each new generation of instruments allows scientists to observe phenomena that were previously invisible. High-speed cameras reveal flashes lasting only milliseconds. Satellites capture faint glows far above the clouds. Radar systems track the internal structures of storms with increasing precision. With each technological advance, the atmosphere reveals new layers of complexity. Events that once seemed impossible or mythical gradually become understood as natural consequences of physics operating under unusual conditions. And yet, even today, there are still aspects of the atmosphere that remain only partially understood. The sky above us continues to surprise researchers with strange flashes, unfamiliar patterns, and phenomena that challenge our expectations. For all our knowledge of weather and atmospheric science, the air surrounding our planet still holds mysteries waiting to be discovered. For most of human history, predicting the weather was more art than science. People watched the sky carefully and learned to recognize patterns. A red sunset might hint at fair weather ahead. Certain cloud shapes suggested rain might arrive by morning. Farmers observed winds, animals, and seasonal rhythms, building knowledge through experience passed down across generations. These observations were often surprisingly useful, but they had limits. The atmosphere is vast and complex, and its behavior depends on physical processes unfolding across entire continents and oceans. Understanding and predicting those processes required something more powerful than local observation. It required mathematics. One of the first people to seriously attempt a mathematical approach to weather forecasting was the British scientist Lewis Fry Richardson. In the early 20th century, Richardson imagined predicting the weather by solving the physical equations that describe atmospheric motion. The atmosphere follows the laws of fluid dynamics and thermodynamics. Air flows according to pressure differences, temperature gradients, and the rotation of the Earth. If those equations could be solved accurately, Richardson believed it should be possible to calculate how the atmosphere would evolve in the future. In 1922, Richardson published a remarkable book titled Weather Prediction by Numerical Process. In this work, he described a method for dividing the atmosphere into a grid of regions and calculating how temperature, pressure, and wind would change in each region over time. The approach was visionary, but it faced a practical problem. The calculations required were enormous. Richardson attempted a single forecast calculation for a 6-hour period using observed atmospheric data. Working by hand with pencil and paper, the computation took him several months to complete. Even then, the result was not particularly accurate. Richardson realized that if numerical weather prediction were ever to succeed, it would require a vast number of calculations performed quickly and simultaneously. He famously imagined a huge hall filled with thousands of human calculators, each responsible for solving a small part of the atmosphere. In an almost poetic sense, Richardson had envisioned a computer long before modern computers existed. His idea remained impractical for several decades. Then, in the middle of the 20th century, technology finally caught up with his vision. During the 1940s and 1950s, the development of electronic computers opened new possibilities for scientific calculation. One of the scientists who recognized the potential of these machines was meteorologist Jules Charny. Charny worked alongside mathematician John von Neumann at the Institute for Advanced Study in Princeton. Von Neumann was one of the pioneers of modern computing, and he understood that computers could solve the enormous systems of equations needed to model atmospheric motion. Together with a team of scientists, Charny developed simplified mathematical models that captured the essential dynamics of the atmosphere. Using early computers, the group performed some of the first successful numerical weather forecasts. Their work demonstrated that Richardson's vision was not only possible but practical. As computers became faster and more powerful, numerical weather prediction evolved rapidly. Modern forecasting centers now operate enormous supercomputers capable of performing trillions of calculations each second. These models divide the atmosphere into three-dimensional grids covering the entire planet. Within each grid cell, equations describe how temperature, pressure, humidity, and wind evolve over time. The models ingest vast quantities of observational data from weather stations, satellites, radar systems, weather balloons, and aircraft. This process of combining observations with model calculations is known as data assimilation. Data assimilation allows meteorologists to construct a detailed snapshot of the current state of the atmosphere. From that starting point, computer models simulate how the atmosphere will change in the hours and days ahead. One of the most advanced forecasting centers in the world is the European Centre for Medium-Range Weather Forecasts, often referred to as ECMWF. Located in Europe, The ECMWF operates some of the most sophisticated weather models currently available. Its forecasts are widely used by meteorological agencies around the world. The centre processes enormous streams of global data and produces predictions for weather patterns up to several days in advance. These forecasts guide everything from aviation planning to disaster preparedness. Yet even with powerful computers and advanced models, weather prediction still faces fundamental limitations. The atmosphere is not only complex but also chaotic. Chaos in this context does not mean randomness. Instead, it refers to systems that are extremely sensitive to small differences in initial conditions. Tiny uncertainties in the starting state of the atmosphere can grow over time, eventually leading to very different outcomes. This phenomenon was famously explored by meteorologist Edward Lorenz during the 1960s. Lorenz discovered that small rounding differences in computer calculations could produce dramatically different weather simulations after several days. His work revealed that the atmosphere possesses an inherent limit to predictability. Even with perfect equations and extremely detailed observations, forecasts beyond a certain time horizon become increasingly uncertain. To manage this uncertainty, meteorologists developed a technique known as ensemble forecasting. Instead of running a single forecast simulation, ensemble forecasting runs many simulations simultaneously. Each simulation begins with slightly different initial conditions that reflect the uncertainties in observational data. By comparing the results of dozens of simulations, meteorologists can estimate the range of possible outcomes. If most simulations agree, confidence in the forecast is high. If the simulations diverge widely, the forecast is considered more uncertain. This approach allows forecasters to communicate probabilities rather than single deterministic predictions. For example, a forecast might indicate a 60% chance of rain rather than guaranteeing rainfall. This probability reflects the proportion of ensemble simulations that produced precipitation. Modern forecasting therefore combines physics, mathematics, and statistics. Supercomputers simulate atmospheric motion. Observational networks provide real-time data. Ensemble methods help quantify uncertainty. Together, these tools allow meteorologists to produce forecasts that are remarkably accurate compared to those of the past. A 5-day forecast today is often as reliable as a 2-day forecast was several decades ago. Despite these advances, the atmosphere still retains an element of unpredictability. Small atmospheric disturbances can grow rapidly. Interactions between storms, oceans, and land surfaces can alter weather patterns in subtle ways. The complex web of processes operating within the atmosphere ensures that forecasting will always involve a degree of uncertainty. In a sense, this unpredictability reflects the same sensitivity that makes weather such a fascinating subject of study. The sky above us is not a simple machine that produces identical outcomes each time it runs. It is a dynamic system where tiny fluctuations can grow into large-scale patterns. Yet through mathematics, observation, and powerful computers, scientists have learned to anticipate much of that behavior. From the early vision of Lewis Fry Richardson to the modern supercomputers of forecasting centers around the world, the science of weather prediction has transformed our understanding of the atmosphere. It allows us to glimpse the future movements of storms and winds, even as the atmosphere continues its endlessly shifting dance above the planet. When we think about weather, we usually imagine it as something uniquely tied to Earth. Clouds drifting across the sky, rain falling from storm systems, lightning flashing within towering thunderstorms. These phenomena feel intimately connected to our planet and the thin atmosphere that surrounds it. Yet when scientists began exploring the rest of the solar system, they discovered something fascinating. Weather is not unique to Earth. Other planets and moons possess atmospheres of their own, and within those atmospheres many of the same physical principles unfold. Heat moves through fluids, winds circulate energy, clouds form from condensing vapors, and storms develop under the right conditions. The details may differ dramatically, but the underlying physics remains familiar. This realization gave rise to a scientific approach known as comparative planetology. Comparative planetology studies planets by comparing their environments, atmospheres, and geological processes with those found on Earth. By examining how similar physical laws operate under different planetary conditions, scientists gain deeper insight into the behavior of atmospheres everywhere. One of the early champions of this approach was planetary scientist Carl Sagan. Sagan recognized that the atmospheres of other planets could serve as natural laboratories for understanding atmospheric chemistry and climate dynamics. Another influential figure was James Hansen, whose early research included detailed studies of the atmosphere of Venus before he later became widely known for his work on climate science. Through these investigations, scientists began to see that the strange weather we observe on Earth is part of a much larger cosmic story. Consider Mars. Mars possesses an atmosphere that is far thinner than Earth's. The surface pressure on Mars is less than 1% of the pressure found at sea level on our planet. Despite this thin atmosphere, Mars still experiences dramatic weather events. The most famous of these are the massive dust storms that periodically sweep across the Martian surface. Because Mars is covered with fine dust particles, strong winds can lift enormous quantities of dust into the air. In some cases, these storms grow so large that they engulf the entire planet. Planet-wide dust storms can persist for weeks or even months, turning the Martian sky into a hazy orange veil that obscures the surface below. The physics driving these storms shares similarities with weather systems on Earth. Solar heating creates temperature differences across the surface. These differences drive atmospheric circulation that lifts dust into the air. Yet the thin atmosphere and lower gravity of Mars produce conditions that allow dust to remain suspended far longer than it would on Earth. Venus presents an even more dramatic example of planetary weather. The atmosphere of Venus is extraordinarily dense, composed primarily of carbon dioxide with surface pressures more than 90 times greater than those at sea level on Earth. Temperatures on the surface reach around 460 degrees Celsius, hot enough to melt lead. High above this scorching surface, thick clouds composed of sulfuric acid droplets circle the planet. These clouds form a global layer that reflects much of the sunlight reaching Venus, giving the planet its brilliant appearance when viewed from Earth. Within this dense atmosphere, winds move at astonishing speeds. At altitudes of roughly 60 kilometers above the surface, the atmosphere completes a full rotation around the planet in only about 4 Earth days. This phenomenon is known as atmospheric superrotation. Despite the slow rotation of the planet itself, the upper atmosphere moves far more rapidly, producing powerful global winds that continually sweep around the planet. While Venus demonstrates extreme heat and pressure, Jupiter offers another kind of atmospheric spectacle. Jupiter is a gas giant composed mostly of hydrogen and helium. Without a solid surface, its atmosphere extends thousands of kilometers deep. Within this enormous atmosphere, powerful jet streams create colorful bands that wrap around the planet. Between these bands, enormous storms can develop. The most famous of these storms is the Great Red Spot. The Great Red Spot is a gigantic rotating storm larger than the entire Earth. Astronomers have observed it for more than 300 years, making it one of the longest-lived storms known in the solar system. Unlike hurricanes on Earth, which draw energy from warm oceans and eventually weaken when they move over land or cooler water, Jupiter's storms have no such limitations. The planet's immense atmosphere provides a vast reservoir of energy that allows these storms to persist for centuries. The winds within Jupiter's atmosphere can exceed several hundred kilometers per hour, forming complex vortices and swirling cloud structures. Despite the alien conditions of Mars, Venus, and Jupiter, many of the underlying processes shaping their weather are the same ones that operate on Earth. Solar energy drives atmospheric motion. Temperature differences create pressure gradients that produce winds. Condensation of atmospheric vapors forms clouds. Fluid dynamics governs the behavior of rotating storms. The equations describing atmospheric motion are universal. Studying other planetary atmospheres therefore deepens our understanding of our own. When scientists examine the sulfuric acid clouds of Venus, they learn more about how clouds influence planetary temperatures. Observations of Martian dust storms help researchers understand how particles interact with atmospheric circulation. Investigations of Jupiter's immense storms reveal new insights into vortex dynamics and turbulent flow. In this way, each world in the solar system becomes a natural experiment in atmospheric physics. By comparing these environments, scientists discover which processes are unique to specific planets and which arise naturally whenever gases move under the influence of gravity, heat, and rotation. Seen from this perspective, the strange weather events we observe on Earth are part of a much broader pattern. Lightning flashing through a thunderstorm, clouds forming from rising air, powerful winds circling the globe, and luminous auroras glowing near the poles are all expressions of universal physical principles. Across the solar system, atmospheres respond to energy in similar ways. Some planets produce dust storms that cover entire worlds. Others form clouds of sulfuric acid or sustain gigantic vortices that last for centuries. Earth's weather may feel dramatic at times, but in the larger context of planetary science, it represents one example among many. What makes our planet special is not that it has weather, but that its atmosphere exists within a delicate balance that allows oceans, clouds, storms, and life itself to coexist. The physics shaping our skies is part of a universal story, written across the atmospheres of many worlds. And when we watch clouds drift overhead or lightning flash across a distant horizon, we are witnessing one chapter of that broader cosmic narrative, unfolding quietly in the thin layer of air that surrounds our home planet.